Here's a nice straightforward sample problem. We're going to compute a line integral. Yesterday, we talked about the overview of our fundamental theorems of calculus, where we integrate a derivative over a set by evaluating the function at the boundary of the set. So now let's get into some details and compute a line integral. So I want to calculate the line integral over C, actually C1 and C2, of some vector field f dot dr. Dot dr is what gives away that this is a line integral and C should be a one-dimensional curve. So dr is going to be a little piece of that curve. And here's our vector field, 3x minus y, I direction, and x in the j direction. I just stole this from somewhere. I think I probably got this one from the book. I like it because it's got two different paths in the vector field. Remember, the vector field is just a vector at every point on the xy plane. So at 0, 0, we've got the 0 vector. At 1, 1, it looks like we'll have the vector 2, 1. And then everywhere along these paths, we will experience a different vector. So even though we have the same vector at 0, 0 and the endpoint 1, 1, everywhere along these paths, we will be experiencing different vectors. We can imagine that the vector field is like the force that's pushing against us. And we want to walk along these two paths, and we want to see which one takes more work to walk along. Maybe that's one way we could think about it. So let's get into the calculations. What we need to do, we're going to be integrating the vector field dot dr. So I need to take this calculation, f dot dr, and evaluate that at all the points along the curve. The same thing that we do every time we do an integral. Take the expression f dot dr and evaluate it at all the points in the set. Then add the results up. This is a really strange calculation. Since we're adding up over a continuum, there's nowhere to put the plus signs, but that's what integration is for. Integration is for adding things up when there's nowhere to put the plus sign. Integration is multiplication when one of your factors is continuously variable. So what we need to be able to do is parameterize each of the curves, because the task always with integration is set things up so that your integral can understand what you're trying to plug in. So we start by parameterizing the curves. Thankfully, that's already done for us. So the curves are already parameterized. The curves have been parameterized for us, but we want to write it in such a way that it makes more sense. So the C1 curve, I'm going to give the position vector R1 of t. The x component is t, and the y component is t squared. So I have these x and y components. These are the things that are going to go into our vector field. At each point, so if I need the point 3x minus y, I need 3 of the x minus 1 of the y. So when we look at these parts, this part right here is saying that x of t is equal to t, and here t and t squared, y of t is equal to t squared. So now I'm going to evaluate the vector field at all the points on this curve. So we're going to evaluate the vector field at all the points on the curve C1. So F will be 3 times X minus Y plus X times J. We just take with the X and Y and figure out what those points are along this curve by looking at the parameterization. The I component is the X and the J component is the Y. This is evaluating the vector field at all the points on the curve C1. Now, this is not what we're adding up. This is a vector field. Oops. Let's make sure that we note that we have now parameterized the vector field, not the whole vector field, just the parts that we care about. This is now the vector field parameterized. So it's a function of t. This is not the vector field everywhere. This is the vector field only at the points along the curve C1 for t between 0 and 1. Remember, our vector field here at 0 is 0, and our vector field at 1, 1 is 2. 3 minus 1 is 2i plus 1j. So 2i plus 1j. This is the vector field at the point 1, 1. Note that if I plug 0 in for t, I get 0. 3 zeros minus 0 squared is a 0i plus 0j. And that's what's going on here. The vector field at the point 0, 0 is the 0 vector. Note that this is the vector field along the curve C1, and at the endpoints, this is the vector field for all the values t between 0 and 1. When t is equal to 0, I get 0, 0. So f at the parameter 0 is the 0 vector. And then f at the parameter 0, 1, 0 for x, 1 for, sorry, 0, not 0 for x. When t is equal to 1, I get 3 minus 1 is 2, and then 1. So if I evaluate the vector field at t is equal to 1, I still get the same thing, 2i plus 1j. There's a different vector everywhere in the xy plane. We only care about the vectors along the curve C1. That's why the parameterized vector field looks like this. Now, this is not what we're calculating. We want to calculate f dot dr. Dr is a vector tangent to the curve. And just like its name suggests, it's just going to be the derivative. So dr now we're going to find the dr for C1, and that's just going to be the derivative. dr1 will be the derivative of t with respect to t is 1. The derivative of t squared is 2t. And the chain rule is still in effect. So this is dr dt. So to find the dr all on its own, you put the dt on the other side. Something we're doing something. Wasn't the chain wheel thing. Sorry. I was thinking of something else. So now we can calculate. Two TJ. That just come from, I took the derivative of R1 of t. So the derivative of t is 1, the derivative of t squared, 2t. So our integral over c of f evaluated at all the points on R1 of t our line integral f dot dr. We're going to integrate the dot product of the vector field along the curve C. So 3t minus t squared I plus 2j dot the dr parentheses. So here's the vector field evaluated at all the points on the parameterized curve, the dot product with dr. Fixed it and still messed it up. So the vector field evaluated all the points along R1 of t. So our integral is now parameterized over dt. We just need the values of t, and t is running from 0 to 1. 0 puts us at the origin, and 1 puts us at the point 1, 1. Now we have a simple integral to calculate. We got to find the dot product of these two vectors. This is still going to be an integral from 0 to 1. The dot product of the vectors is going to be 3t minus t squared times 1 plus t times 2t dt. So here we are calculating the dot product. So I find the products, I find the sum of the products of the corresponding components. 3t minus t squared times 1 plus t times 2t. We can simplify from 0 to 1. We get 3t minus t squared plus 2t squared. So 3t is going to be plus t squared dt. So our line integral has become this regular integral. The integral of 3t is 3/2 t squared. The integral of t squared is 1/3 t cubed. Evaluate from 0 to 1. So now we integrate. and then evaluate at the endpoints. So 3/2. Once we have the parameterization, it all kind of falls into place. You have to know where the torque goes. The parameterization is where we decide what X and Y look like. That goes into the vector field. So our vector field is just evaluated at all the points along the curve. Then it's just plug and chug. Any questions? This was the line integral along the path C1 from 0, 0 to 1, 1, following this parabola. Let's follow the other parabola. So we have a different parameterization for the path C2. So for the path C2, our parameterization was switched around. We have t squared I plus t times j. Once again, for t, going from 0 to 1. So it's just another parabola from 0, 0 to 1, 1. They are not. In the previous one, y was equal to x squared. In this one, x is equal to y squared. The path is the same shape, but the vector field, the vectors that we're going to collect along C1 and C2, those vectors are going to look different. So the paths, one of the paths is y equals x squared. The other path is x equals y squared. Because I'm not very creative. But the vectors that we're going to experience in each of those two different paths will be different, right? So think about the vectors at this point. Think about the vectors that we have at the point. On C1, we have this point 1/2, 1/4. If we evaluate the vector field at the point 1/2, 1/4, I get 3/2 minus 1/4, so 5/4, and plus x, which is 1/2. So at this point, halfway along our path, we are experiencing the vector 5/4, 1/2. But if we look at the vector here, when t is equal to 1/2 along the path C2, we'll be at a different point, and so the vector field will be different. So the vector field at that point, which is going to be 1/4, 1/2, will be 3/4 minus a half, so 1/4 and 1/4. So the vector field here will be pointed in this 45-degree angle, and the vector field here at this point will be 5/4 and 2/4. So it'll be at a slightly lower angle. So where the paths have the same shape, but the vectors along those paths are going to be different. So the other parts that we need are going to be the vector field evaluated at R2. So the vector field evaluated at R2. So here, the x is going to be t squared, and y is equal to t. So my vector field will be 3t squared minus t I plus the x, which is t squared j. And this is for t from 0 to 1. That's not the vector field everywhere. That's the vector field evaluated at all the points along our parameterized curve. And I also need my dr. So the derivative here is going to be 2ti plus 1 times j dt. So my line integral. I'll have my vector field evaluated at all the points on the curve. Dot the dr. I just took the derivative of each of the components of our RT. So here's f at all the points that we care about along with the x and y plugged in. And here's the dr, here's the direction vector along that curve. And this is how we parameterize the curve for t between 0 and 1. Everything is still in terms of vectors, but there's a dot product. Calculating that dot product will get us to a function of t. So we'll have 3t squared minus t times 2t plus t squared times 1. So we get algebra. 6t cubed minus 2t squared plus t squared. So 6t cubed minus t squared. Now we can integrate. The integral of 6t cubed is 6/4 t to the fourth minus a third t cubed, evaluated from 0 to 1. So this time it's going to be 9 minus 2, 7 sixes. So we get a different integral along a different path. Lots of ways that we could think about this. We can think about the work. This one, maybe one is more work or less work, depending on how much of the wind you're trying to go against or how much the wind you're trying to go with. Imagine going from San Francisco to San Jose. We got two different routes. We can go 280 or 101. One of them will have more traffic. One of them will have less traffic. More gas, less gas. One will use more time. One will use less time. The vector field will be different at all the points along 280 and all the points along 101. Maybe that's why I did this problem, because it looks like the peninsula. It's kind of like at a different angle. How's everybody okay? Is the correct answer. We have calculated exactly 2 line integrals like your entire mathematical career. So you're supposed to be like, oh, I'm not too sure about this, because that's how learning stuff goes, right? You don't get to walk into Giants spring training and say, I'd like to apply for a job on the Giants baseball team. They go, great, what is your experience? I've watched some baseball on television. I go, oh, well, you're up against this guy over here who's been playing baseball since he was 4 years old, to the exclusion of everything else. But yeah, suit up. You've only watched like one baseball game, and it was super boring because it was a math baseball game, and you're just like not into it, and there was no money on it, no advertisements, and it was going slow. You need to have a shot clock or a pitch clock. I guess that's a thing now. I don't know. I don't think the change is going to do what people think the change is going to do. No one is like not watching baseball and saying, baseball's too long. I would watch it if it was shorter. Right? Maybe people have said that, but I highly doubt that those people are showing up to baseball games now. They're like, oh, what's this? They're going to be hitting more faster? Well, now I'm in. I mean, no one's doing that. You're just pissing off fans that don't care how long it takes, that don't care that games are like 3 hours long. Now, just moving things along is one thing. The umpire has always had the power to move things along. If he thought the pitch was taken too long, he could be like, "Oh, speed it up, Chief, let's go," and start throwing and start just telling him to speed it up. What I don't like is that I guess there's one. I heard this on April Fool's Day, so maybe it's not true. You can't throw over to first so much. It's like, what the fuck is that? You take a valid strategy, you can't do that anymore. Now, right now, I'm like, oh, ooh, I don't like this, but maybe if I was like hundreds of years old, I wouldn't have liked the part where they said, well, the batter could no longer call for a low or a high pitch. That used to be a thing. You would step up to the plate and you're like, oh, dude, throw it high. And if you throw a low pitch, even if it was in the strike zone, you're like, oh, no, I didn't want that one. High pitch, please. And you're like, oh, man, so he's got to throw 4 balls, or like throw low, 4 low, no walk. It's like, oh, no, 8. 8 balls was a walk. It used to be 8 balls was a walk. And I'm sure people are watching cricket and like saying, oh, this is just going to just go too fast. Cricket, I don't know, there's like one match of cricket. Is it still going on after 110 years? Anyway, I don't think it's going to capture the audience they think it's going to capture. People are just going to be annoyed. They're not going to do anything about it. They're just going to be like, I don't like this. And then in a couple of years, everybody will forget. You know what I mean? You know why gas is expensive? Because we keep fucking buying it. All we do is complain. We don't stop buying gas when we have the power to do so. We just like, oh my gosh, it's $5 per gallon. I can't believe it's $5 per gallon. I'm going to start walking everywhere. No, you're not. You're going to keep buying the gas. And so they're going to charge more for it. And then people be like, oh, I'm going to get a horse. I'm like, oh, dude, as someone who owns a horse, it is not cheaper than $10 a gallon to own a fucking horse. It is not. If the car runs on liquid paper, then maybe we have an issue. But no, it is way more expensive to have a horse. It's only got 1 horsepower. What are we talking about? Oh, horses. The horse is super pretty though. So there's that. Her name is Karina. And she's a very fancy theory. So we have only calculated 2 line integrals, but the procedure is always going to be the same. We're going to want to take our curve. Right now we had a parameterized curve, but it could be that we have a curve described in a different manner. So we could just have a description of our paths. So C3 is a line from 0, 0 to 1, 1. We would have to parameterize that. Instead of being given a parameterization, we have to figure out what the parameterization is. Since I've already used up my parabolas from 0, 0 to 1, 1, I go with C3 is the line from 0, 0 to 1, 1. Another popular choice. And of course, our favorite, a circle. A quarter circle from 0, 0 to 1, 1 with radius. So that would be just another 2 more ways from getting from 0, 0 to 1, 1. So in this case, the parameterizations aren't given to us. We have to figure out what they are. But then the procedure would be the same. We figure out the parameterization by figuring out the X and Y coordinates, plugging those into the vector field to figure out exactly what points we care about, or which vectors we care about, and find the dot product with the dr along the path. So I calculate an R3 and an R4, calculate the DRs for each of those. Evaluate the vector field at each of those XYs. And then it's the same thing. Then the simple integral integrated from the end. What's that? I don't ride the horse. I'm only married. I only married into equestrian. So I am a squire as far as I hold stuff. That's my job. Okay? That's it. I hold stuff. I hold stuff, not horses. I'm not qualified to like hold a horse. I'm not qualified to be a post to hold a horse. I don't know enough about it. I'm not going to horse college. I'm just on the job training at the squire. I know that when I'm at the barn, you don't run, but I knew that already. Horses don't like that. If you start, like if you're at a barn and there are horses around, you don't want to run. If it's an emergency, you just kind of like walk with purpose. Because the horse sees you walking with purpose, and like, oh, that's cool. They can have somewhere to go. But if the horse sees you running, I'm like, oh, fuck, we got to start running. Why? Don't know. There's running going on. We're really good at that. You don't have to outrun whatever's chasing that dude. You just have to outrun that dude. And then they'll get upset. I mean, they're prey animals. What do you think? What do you think? Left side? Left side, yeah. That's because the other job I'm qualified to do is mountain block. I can stand like this and lift up slowly. And you know why that is? For the most part, we're right-handed. That's where your sword is, over here. So you don't want to get up that way because your sword would fall out. So you get up on this side. And if you're left-handed, it's like, I'll just give you switch. You go cowboy style, just jump off from the back of the horse. I'm just kidding, don't do that. That's how you get kicked. Oh. Any questions? Comments? All right, so I want you to parameterize these two curves and then calculate those line integrals. I moved the center of the circle from to 0, 1. So unless you want to shift the entire vector field 1 unit down, just figure out how to move your parameterization up 1 unit. If you're wondering, that sounds like something that you're going to do both of tomorrow anyway. Yeah, probably. Because that's the kind of stuff that we do around here. Transformation is like one of the most important tricks of math. Add 0, multiply by 1, transform, move stuff around. That's it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.